Okay, so thank you very much. It's a great honor to be able to be here and wish Maxime a happy birthday. Yeah. Yeah. Well, what I'd like to talk about today, I'd like to say, Maxime, as you all have known and said many times so far, has been at the origin of a number of conceptual revolutions, I think. In a lot of different subjects, in fact. And what I'd like to talk about today is another one of these examples on the subject of basically character varieties, or spaces of representations. So the space of representations. So let's let X over C be basically a curve. Maxime keeps asking me, what about higher dimensional case? But okay, let's for these questions, these questions are already mostly happening for curves, and we don't really know what to say further. I don't think for higher dimensions yet. Anyway, so let's take a curve, and so we should think of it as basically being either a compact curve or some kind of open curve, but we keep some control over what's happening at the puncture points and so on. And as I think many of you know, an important part of what's going on is also happens for irregular connections and stuff like that. But I'm maybe not going to make that much of a distinction for that here. And so the space of representations, let's say into SLN, so let's say R. This is an affine variety. Usually, called also, by the topologists call this the character variety. So in particular, it's open, so it's non-compact. And so I think there's recently been some kind of conceptual revolution. And how we can look at the points at infinity. Unfortunately, I don't actually understand this very well. And also I'd like to thank Tom Bridgeland, because I think in his talk yesterday, he said a lot of things which one should say here. Let me just, first, before getting started, write down some of the people. So obviously Kontsevich, Zeubelman is. They have a series of papers which are really at the origin, I think, of this. Also Gajodor Mornitsky. Let me apologize, especially since I'm on film. Yeah, okay. I'm going to be forgetting lots of people here, so I'd like to apologize to all the people who I might forget here, which are numerous, especially, as I said, being on film. Then I'd also like to write, Bridgeland Smith. Then there's also people which are basically coming from 3D topology or low-dimensional topology, and other similar types of directions. But for example, Richard Wentworth. And there's a whole group of people working, roughly speaking, around Francois Labouille. maybe I'll say Lofton, and other people working with them. Ian Lee, for example. Well, their work is based on stuff which we've actually been using a lot, which is a work by Parot. And Parot, I think, was working with Frédéric Paulin, using Kleiner-Lieb theory. And this whole thing is actually also goes back to Morgan Shalin compactifications and so on. And also, I'd also like to mention Thomas Hausel and his co-workers, Rodriguez Villegas. Letelier, and so on. And then there's also a number of recent people, which I'm sorry I don't know. For example, Tom mentioned in his talk a certain number of people, Ikeda and some other people. But there's been several different recent preprints on arXiv. I'm sorry, I just didn't, collect all this information. And I'd also like to say that what I'll be talking about here, aside from the sort of global picture, which is maybe older, but the actual theorems or observations, theorems, conjectures, and stuff like that are joint work with Lun Mill, Alex Knoll, and Pranav Pandit. And I'd also like to say, this was on some visits to Vienna, so there's also a number of other people in the group in Vienna which we were discussing these things with, and I think we should particularly put Fabian Heiden, who was helping some discussions. Okay, and we have a preprint on arXiv, so I'll be trying to draw some pictures here, but you can also see the much better versions of the pictures in the preprint. Okay, so let me just get started. So to get started, I'd just like to draw some pictures. These are not the pictures in the preprint, but just like to draw the sort of a global picture of the structure that you have on moduli spaces of representations. So let's sort of put that over here. So I'd like to make a box, but instead of making a box, I'll just leave this top open, okay? So this box is representation. Okay, the next box is connections. More precisely, vector bundles with integrable holomorphic connection. Okay. The next box, which I'll put over here, is Higgs bundle. Now I'd like to connect these together a little bit. So this is the Riemann-Hilbert correspondence. And here, well, we have the solutions of the Hitchin equations, which give the correspondence here. But in fact, what I'd like to draw here is actually more the moduli space of lambda connections. Let's draw it this way. Okay, so we sort of have a coordinate here, which is lambda. So let me put in quotes that lambda is sort of equal to h bar, but I'm not really sure. I mean, you guys know this much better than I do. Sometimes people put an h bar in here, and I guess the lambda coordinate is often somewhat related to h bar as it occurs in, in quantum mechanics. I'm not sure whether it's really reasonable to think that this parameter lambda, which is kind of a universal parameter that's showing up in math, whether this is really equal to h bar, or is it just that it plays a similar role in some cases? And so this is lambda equals 0, and this is lambda equal 1. We have a GM action on the space of lambda connections which scales lambda, and that's why I'm drawing these like this. But the images of the orbits here, the images of the points here, their orbits all go to the sort of ground level state in Higgs bundles, which is the nilpotent cone. Okay. And so I left a little bit of room here for the Hitchin map. The Hitchin map maps the moduli space of Higgs bundles to a vector space. Okay, so let's just call this AN. I would call it, I guess you could call it B as the base of the Hitchin vibration. B is going to show up a little later for a different thing. So, and this map is proper. And for example, these guys go to 0. The nilpotent cone here is just the fiber over 0 in the Hitchin map. Whereas this space is affine. So let me just say with respect to what Richard was saying in the previous talk, I gather that this is a little bit of an analogy which is considered by you guys, maybe, which is the fact that all through this is a complex analytic isomorphism. So if you have an affine variety, it can't actually have any compact subvariety. And that's preserved over to here because it's just the same complex analytic subvariety. So up until here, there's no compact subvarieties. So I gather that there's a little bit of an analogy with this transversal section to the algebraic, to the Noether-Lefschetz locus that Richard was talking about, in the sense that here we have something which has a lot of compact subvarieties because in fact it has a proper map, so all the fibers are compact subvarieties. But it sort of deforms to a guy which has no compact subvariety. The nearby fiber here is just the same as this space. So I'm not sure what to do with that further, but I think that's an analogy which you need to take into consideration here. Okay, so well, the fact that this is an affine variety means that we have that it's open. That's why I left this open up here. And so we can think of trying to compactify. Okay, now what's a compactification going to look like? So I'll draw this. This is actually an example which you can actually calculate. The only one which I know how to actually calculate. In an example, the compactification looks something like this, for example. So the compactification, say with a normal crossings divisor, is going to have a lot of different components, and they're going to meet in subcomponents and so on. Okay. Whereas on this side, we can also compactify, but in a different way. So in the moduli space of Higgs bundles, we have a C-star action. This is the trace on the fiber lambda equals 0 of the C-star action, which trivializes the rest of the space of lambda connections. And so we can just throw out this piece and divide everybody else by C-star. Okay. So we can just add at infinity here a guy which is just the quotient of everything except the bottom here by the action of C-star. Okay. If you think about it a little bit, that's actually not it's a smooth, I mean, if this space is smooth, which it happens in many cases, then that's basically going to be a smooth divisor. It's not actually exactly smooth because it has some orbifold points. The orbifold points are actually interesting too because they correspond to Higgs bundles which are invariant by some finite subgroup of C-star. And those include things called cyclic Higgs bundles, which are being used by some people now. But if you think of it as an orbifold compactification, then the divisor here is actually smooth. Okay, and this just goes to the, to the sort of Pn minus 1 at infinity of this affine space. Maybe that's cheating a little bit. This affine space actually has the action of C star is actually weighted here. So this is sort of a weighted, maybe, projective space. Now it turns out that you can use this picture here to get the same kind of compactification here. In fact, the compactification has exactly the same divisor. So these guys are the same. Which is to say, the points here are just, again, points in the space here up to C star invariance. And we can actually see how that works as follows. So if we choose a point out here which is not on the nilpotent cone, then we take a section going out to this point. Then we translate this section back by the C star action. So you can see what's going to happen here from this picture. When you start translating back this section to here, you're going to get a curve which goes out to infinity. Okay? Maybe do we have some color? Let's sort of shade it as it gets closer and closer to infinity. And that's corresponds to the shading here by going out to here. And so not only do we get a curve here, but we actually get a parameter too. Let me call this parameter t, which is basically 1 over lambda. So if we're calling lambda h bar, it's 1 over h bar. Well, that's in quotes. So a point at infinity, if we can think of a point at infinity here on this divisor as being a point in the moduli space of Higgs bundles, and going towards that point inside here corresponds to just going towards this point sort of horizontally in the moduli space of lambda connections. So from that, I mean, of course, you have to do the geometrical argument, but from that, you can see that the divisor is going to be just the same here and here. So from this point of view, we'd like to think of the behavior at infinity in these two different spaces as being roughly speaking the same. That's obviously a vast oversimplification. But we can think of it as being roughly speaking the same. Okay. Now, I'd like to draw, furthermore, a sort of a cylinder around this guy. So let's think of taking a neighborhood of infinity. Now, the cylinder over this guy is going to go to, a neighborhood of infinity in the Hitchin base. So let me just say my picture is actually, I'm actually drawing the picture in the case where this is A1. It's just the affine line. So for the picture, this is actually a disk, okay? So I don't really want to let's think of the projective line as being sort of in the middle of the disk. In any case, the boundary of this neighborhood at infinity is actually going to be a sphere. It's a sphere with a kind of Hopf vibration to Pn minus 1 in the general case. It's just a circle in the case of the base has dimension 1. And again, this picture is also a picture. This is actually a relatively accurate picture in this case of where the Hitchin base has dimension 1, where the spaces have dimension 2, complex dimension 2. And it turns out that this is, I learned this in a paper from Goldman and Toledo. This is a triangle in a cubic surface. Okay. So that's a very classical thing, Fricke-Klein or something like that. But if we think of taking the neighborhood of this guy here, it doesn't look a lot like the neighborhood here. But actually, the point is that if you think about it a little bit, it really does look a lot like this neighborhood, in the sense that here we have if we look at this configuration of divisors at infinity, we see a circle. Okay. If we look over here, we also see a circle. Okay. So just from this picture, you can see that what's probably happening here is that circle there is going to go to this circle here. So when you go once around a point in a little disk in this picture, you're going around an entire divisor of stuff over here. And
Carlos, for SL2, there is a certain boundary of the Teichner space. Is that what you're talking about there? Or
I'm not sure, but I'm going to be getting to that. Getting to say something more somewhat closer to that. Before getting there, let me just say a couple of things. So one is that we can conjecture that the incidence complex of the divisor at infinity in the divisor infinity at the character variety is a sphere. And that the correspondence, this maps by some kind of homotopy equivalence to the sphere at infinity in the Hitchin base. Okay. So Maxime keeps telling me that this is actually a theorem, okay? So I'm not quite sure what the hypotheses of the theorem version of this statement are. But in any case, I think, and it's stated in a phrase in, Jan pointed out, it's stated in a phrase in their paper, at least something like this. There's also a theorem which says something a little bit like that in a paper by Richard Wentworth, I think. And I think that, what you said about the Thurston boundary and so on is fairly close to this. This conjecture is only just motivated really by this picture, in fact.
In the case when you have a triangle for the representations, what's the boundary?
Yeah, so if you think, okay, we can think about this a little bit more clearly, but how are you doing for time? You can make this correspondence a little bit more precise in this case, in this example, which is that if you think about
when that one's a triangle, what's the boundary of the middle one, of the connections?
Well, as I said, this is pretty much the same as this guy, I mean, roughly speaking.
Multiple P1 or what?
Well, no.
Connections.
Well, okay. So the point is, in the Hitchin moduli space, the fibers of this map are elliptic curves in the two-dimensional case.
Yeah.
So we're going to have these, but in general, the general fiber is in an abelian variety in any case. So the fiber is basically going to be some, let's call it abelian variety, or some kind of Jacobian. In fact, it's more of a prim or something. Okay. But it's a torus, okay? It's a complex torus. But in this one-dimensional case, there's no problems with discriminant loci, and in fact, it's always the same elliptic curve. And indeed, when you go once around, that does a -1 on that elliptic curve. I was telling you that yesterday, actually. When you go around here once, that does a -1 on this elliptic curve. Okay. And now, if you look over here, the fiber think of squishing the neighborhood of these three lines to the lines themselves. Okay. The neighborhood of a point here is, it's a delta star cross delta star, basically. So homotopically, the punctured, the corner neighborhood of the polydisk that goes around this point is S1 cross S1. And that's going to correspond to the elliptic curve, in fact. And what about pieces inside here? Pieces inside here, you have to remember that this line is actually a P1. So between these 2 points, we have a GM. So there's already a one-dimensional circle direction there. And then there's the other dimensional circle direction of the neighborhood of the disk. So those sort of combine together to, again, make an elliptic curve. And you can sort of see in this example that this whole thing follows around. And if you follow along these coordinates, you exactly get a -1 also on the torus. If you identify tori, 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 you get -1. I mean, it's something like. I forget why I didn't do this calculation. You have to do this calculation. There's a matrix with 3 1s, 2 1s, a -1, and a 0 in it, whose cube is -1. That's going around this guy in that example. I didn't want to do too much detail on this example for several reasons. One of which is that this example is, I think, totally subsumed as a trivial baby case of what Jan and Maxime do. But okay, so maybe just to continue with the picture a little bit. So we can see here there's some interesting regions which are the neighborhoods of crossing points, okay? And some other interesting regions which are the neighborhoods of things which are not the crossing points. Now, you can actually calculate, again, in this example, you can actually just explicitly calculate with the equation. For certain values. This example is the case of P1 minus 4 points with a rank 2 system and some conjugacy classes at the 4 points. For some special values of the conjugacy classes, you can actually calculate the map and see what happens. What actually happens is that these regions here, which are small regions here, go to entire sectors over here. More precisely, there's 3 maps, like there's 3 walls, so these are really the walls. Then let's sort of look at the pullback of those walls in the cylinder. And it's the regions which are not on the walls here, which correspond to regions like this here. So basically this map from one side to the other has this property that it's exchanging big regions and small regions. Okay? I think that's what I would say, I mean, at least as a first epsilon approximation is really the new conceptual thing which appears in Kontsevich-Soebelman. So they basically have a picture like this in general, and these are the walls of which the wall crossing formula is talking about. So let me just mention here, as far as this is concerned, which is that this conjecture can also be viewed as a geometric version of the P equals W. Of the P equals W conjecture of Thomas Hauswell and his co-workers. Why do we say that? Because basically the map from the divisor, the map from the neighborhood of infinity onto just the real incidence graph on this side. Okay? So take the incidence variety and just take a real simplicial complex. Okay? That's the thing which we're conjecturing is a sphere here. So that's supposed to go to the map here, which just maps you to the sphere at infinity in the Hitchin base. Okay? So it's some kind of vague statement that's saying sort of weight stuff, because, this map to this real incidence complex sort of corresponds to some top or bottom piece of the weight filtration. Okay? The map that induces on cohomology is going to be the highest or lowest piece of the weight filtration in the cohomology of maybe of a neighborhood at infinity of the character variety. Whereas this piece, this sphere, if you're looking at the sphere in infinity but in the Hitchin base, it's clearly the cohomology class there pulls back to something which is clearly somehow related to the Leray structure for this fibration. Okay? And Hauswell's conjecture is a more precise conjecture, saying relating perverse Leray filtration on this side with the weight filtration on this side. So I don't know, whether you can. I mean, this is only, a tiny piece of both sides, if at all. So I don't know. One could ask, can we really geometrically say that the rest of this conjecture corresponds to some geometric picture? I think that's probably actually feasible once we really understand the wall crossing picture here. I mean, you might say maybe wall crossing should actually imply this P equals W conjecture or something like that. Let's see. So what did I want to say next? So this is kind of the global picture here. Now, the next thing I'd like to talk about, maybe I'll leave that up here, and since the tradition here seems to be to use the sideboards. So let me just leave that up here. Now, what I'd like to talk about now is well, we were just in Vienna. We were just trying to sort of understand this picture and understand the relationship with things like stability conditions and stuff like that. Oh yeah, maybe I should say that before. So as I said, I don't really understand this, and I think Tom actually gave a better discussion than I could here. But what's the kind of zeroth order output of the papers by Kontsevich Soibelman? Says basically that the Hitchin base should be considered as corresponding to a space of stability conditions. This is really more of a philosophical. Yeah. I don't know. Well, I mean, we've been working on trying to figure out how to get the category and everything from this picture, which we haven't found yet. But maybe you guys know how to do it. But maybe we didn't see how to prove that. But I mean, in any case, I think I'm not sure about it. Okay, maybe considered as corresponding to or is equal to. What I'd like to point out, the point I'd like to make here is that, in fact, the idea is that we have these structures. So on some kind of stab of D, we have a structure of walls. Also, maybe one thing to say here, which Tom said yesterday, is that we have to integrate this whole thing over the moduli space of curves. Okay, we're not supposed to just fix a single curve, but we're supposed to put those in together in a family. And so in some cases, this is the result in the paper of Bridgel and Smith.
It's not necessary. It's for a large group. You add small percentage of parameters and it's a very curve. The dimension for the space is much larger. You never get the full on the space if it's group larger than simple.
Okay. So you mean there'll be other stability conditions which are not covered by this? Yeah, okay. But in any case, in the space of stability conditions, we have some walls. So if this guy is sitting inside the space of stability conditions, we'll, in any case, have walls which are the intersection of the walls into here. So we're going to have some walls, okay? And these walls are the things which I drew in the example. And the idea is that these should be maybe let's say the walls. Maybe let me say the chambers. In fact, the chambers should correspond to points in the character variety in the compactification of the character variety. So points over here. So chambers over there should go to points over here. And the walls, I gather, are supposed to correspond to P1s, basically. So, in general, I don't think anybody knows how to write down equations for this in any good way, in general. Maybe there I'm talking about the compact case of compact Riemann surfaces. In the open case, we have the cluster coordinates, so we can do a little better. I'm not sure whether it's very clear what the higher dimensional pieces look like in here. Maybe you know. But in any case, what Maxime points out is that we have these P1s, which join together points. So part of the idea, I think, is that on a given P1, there's only going to be 2 points. Is that accurate? Yeah. So basically, if we look at the stratification that you get from compactifying the space of representations, you'll have some points, which will be the lowest dimensional strata. Between the points, they'll be connected by some P1s. Those P1s are supposed to correspond to codimension 1, real codimension 1 walls over here. Okay. When we go from here to here, we do half the dimension. So things which are complex dimension 1 there could well correspond to real codimension 1 pieces here. Yeah, so now the SL2 case, the case of some kind of character varieties with coefficients with SL2 coefficients, has been treated by a number of people and in lots of different ways. So it's so let's say well treated. Among other things by Bridgland Smith. And in this case, so this is kind of the start of our discussions that we had with in Vienna. In that case, the Hitchin base is equal to a space of quadratic differentials. Okay. A quadratic differential Q just corresponds to the spectral curve y squared equals Q. In some kind of cotangent bundle of X. And a big role is played, an important role is played by the foliation. Say a real part of Q equals 0. Okay. And this actually goes back to Thurston theory and so on. Let's see how we're doing for time. Let me just explain maybe. So underlying this situation, there's something called a WKB question. So we can draw the WKB question here, basically. So here I drew a curve. Here I took a horizontal curve going out to a point in the space of Higgs bundles. If we translate that back into this picture, we get a nice algebraic curve in the moduli space of connections, which goes out and has a nice transversal structure to the divisor at infinity. And in fact, we have this canonical parameter. So at the divisor at infinity, there's sort of a good way of measuring how close we are to the divisor at infinity. Now, if we take that and look at the monodromy representation, I think this is what corresponds in Tom's talk to the place where he said, okay, let's take a complex projective structure and look at its monodromy. So we look at the monodromy, but here we can just say, let's take a connection and look at its monodromy. Then this is going to give some kind of weird path inside here. Okay. So this is going to give some kind of path, let's call this rho of t. And the map, so we have a map from basically C, or some neighborhood in infinity of C, into T mapping to rho of T. And this is actually what's known as the WKB problem. And so it turns out that this function has some very nice properties, which I think we could sum up as saying it's the example of Voros resurgence. Maybe without writing this down on the board, I can say more precisely. Here we can, even though we don't really know the equations, we can write down some coordinates, the Procesi coordinates, which are just the traces of the representation applied to some group element. And so we can think of, this is an affine variety, we can embed it by some coordinates. If we look at those coordinates as functions of t, then we can take the Laplace transform of those functions of t. The Laplace transform of those functions of t has a very nice analytic continuation property. And that's Voros resurgence, basically. So this is a very exponential kind of a curve, but it does have some sort of hidden regularity properties. And what Gaiotto and Mornitsky say is that they analyze.
And what's the curve in the connections? You're just scaling the connection?
Yeah.
We're taking a curve here, so we can be. I can be more precise about this. Let's say a typical example. Let me write that down here. A typical example of the connection is, E. Say VT is just a trivial bundle. Nabla T is equal to D plus some. So let's take some kind of initial connection where if we take the trivial bundle here and we just add a diagonal thing here. Well, okay. Let's not have the trivial bundle, just some bundle, okay. Let's just choose some connection nabla 0 on the bundle E, and then we add a multiple of the Higgs field, okay. So E, so the limit over here is E phi. This is one typical example. There's different ways of, if you've got a point here, there's different ways of getting a horizontal section that goes out to that point. But roughly speaking, we expect that the behavior over there is sort of the same. That's going to give you a number of different ways of having a family here that approach this point at infinity here. One, sort of the easiest conceptually easiest way to write one down is to just take a bundle. Assume that we have a Higgs bundle whose underlying vector bundle admits a connection, which is not always true, in fact. But assuming that that's true, then we can just choose some connection, then add a large multiple of some of the Higgs field. So this is what's called singular perturbation, and this is where this WKB thing comes in. We're taking a connection which has the property that it has a large algebraic term. Okay. In terms of differential equations, that's what the same thing that you're going to get if you do something like, this h bar squared d by d z squared plus the potential. If you turn this guy into a matrix form, to a 2 by 2 matrix form, and then divide by h bar, then you're going to exactly get a 1 over h bar here, basically. Okay. And so the WKB problem is just in general what happens when you have a system of ODEs like that has a large parameter in it. Okay. So then there's the whole question of, Voros resurgence is sort of what happens when you try to do exact WKB approximations. Well, so what happens in this SL2 case is the following, which is that you can actually say what's going on a lot more clearly for this WKB problem. So the WKB problem in the SL2 case, which is, okay, I'll just draw this picture. We have the foliation defined by the quadratic differential. So in the case of a generic quadratic differential, this foliation is going to have just triple points here like that. So these are points where the quadratic differential looks like z dz squared. Okay. Now suppose we have a point here and a point here. And we'd like to calculate the transport for our connection from the point P to the point Q. Okay? Then, am I going to succeed here? Let me do this with color. Then we take a path joining P to Q. If we take a path which is transverse to the, what's going to happen here? This is not good. If we take a path like that, which is transverse to the foliation, so gamma if we take a path which is transverse to the foliation, then the transport for the connection, so T PQ of T, it's rho of T applied to a group element, but you should actually think of it as you should look at the fundamental groupoid rather than the fundamental group. So we should look at the transport for the connection going from the point P to the point Q, but the connection depends on T. Then this is going to look basically like e to the some constant times t, and the constant is going to be the length of the path transverse to the foliation. Okay, so the exponent of the transport matrix is the path length transverse to the foliation. This is not true if you take a bad path which is not transverse to the foliation. If you took a path like this, then if you try to calculate the length of the path transverse to the foliation, then this real part of Q changes sign as you go past this point. You can see from differential equations you're supposed to be taking the absolute value of this guy. But this is going to give you the wrong answer because we sort of went too far up and then too far back down again. Okay? So this doesn't give you the right answer. It just means that if you try to integrate the ODE along this path, it looks like it would have this exponent, which is the length along this path, but actually a whole bunch of stuff is canceling out due to moving the path from here to here. Okay? Maybe that's what's called quantum tunneling, possibly. Okay, so should be stopping pretty soon. I think all this is, I'm not an expert on this by any means at all. I think we can say that what's going on in Kontsevich-Soibom and which is now, this paper of Bridgel and Smith and so on, there's this notion of BPS states. And I sort of purposely drew this foliation as to be close to a foliation which is going to have a BPS state. So if you rotate things a little bit, you can see that there's going to be a stage where the leaf coming out of this singular point equals the leaf going into this singular point. When you go through that stage, then this blue path, you have to sort of change the direction of the blue path as you go across that state. Okay. So our idea was to say that somehow or other the geometry, but we don't know how to make this precise in fact, but that somehow or other the geometry of the BPS states and so on, so we'd like to say that the geometry of the BPS states corresponds in some way. And this is supposed to be the thing which is governing in some way, which I don't understand, the wall crossing formulas which fit into this global picture. But the geometry of the BPS states should correspond to looking at the tree, which is the quotient by the foliation. Which is another way of saying it's the space of leaves of the foliation. Okay, so let's call that T. And we have a map, just the projection from X to T. Okay. So this guy is a tree, and this map, let's call this H. H is what's known as a harmonic map. Okay. And in fact, it's a harmonic phi map, where phi in this case is the quadratic differential, but in general is the spectral curve. Just phi1. So it's sort of the square. In this case, it's just the square root of q. This quadratic differential, if we take the square root, that's a differential, but it's only defined up to sine. Okay? And the differential of h is equal to the real part of phi, basically. That's well defined because there's no well-defined direction on the tree, just up to plus or minus 1. Okay? Now we have a situation where, in this SL2 case, the quadratic differential itself leads to this map from x to t. Okay? Let's call this t phi. This tree only depends on the quadratic differential itself, okay? Now,
Maybe universal cover.
yeah, okay, sorry. Universal cover. And this whole thing fits in, which I don't have time to talk about this too much, but it fits into the theory of Perot and so on, which is really going back to the Morgan-Shalen compactification, in fact, which is going to say that if we look at a sequence of connections, then we're going to get a limiting harmonic phi map x tilde into some tree t. So let's call this t omega because it depends on the choice of ultrafilter or something like that. Okay. And this is for those of you who might want to look where that is in our paper or know what it is yourself or something like that. It's sort of the cone. It's cone omega. It's the asymptotic cone. Underlying here, I mean, again, you'd have to write this down, but as many of you know, the underlying, especially the Hitchin correspondence, there's this notion of harmonic map to a symmetric space. And if you're thinking, oh, can we think of this tree as being the asymptotic tree with, on some kind of Gromov boundary of harmonic maps to symmetric spaces? The answer is yes, and in fact, that's the way you get it, and that's what Perot's theory says. But now, what's the relationship between this guy and this guy? It's just that this guy has an obvious universal property, which is anytime you have a harmonic phi map from x tilde into anything, into any tree, it obviously has to factor through the space of leaves just because phi is constant on the real part of phi is, the real part of phi is 0 along the leaves, so the harmonic map has to be constant on the leaves, okay? So this has a universal property like that. So now this is what we wanted to look at in the higher rank case. Why did we want to look at this? Basically for a number of many of these reasons here. Notably, I guess the idea is that the stability condition is supposed to somehow or other just depend on the choice of point in Hitchin base. So whereas this limiting tree here might depend on more than just the point in the Hitchin base. So we'd like to get a structure which only depends on the point in the Hitchin base. So now in our work, we've been looking at how to extend this to the case of just SL3, okay? So, SLR or we don't actually have anything. We don't know what to say here. No, sorry. I guess some parts of the argument work for anything. So basically, Perot's very nice paper extended to groupoids, extended in a relatively simple way to groupoids. Yields the the following thing, that if we have a phi, which is a, if we have a WKB question, so let's say delta t equals delta nabla 0 plus t times phi. So if we have a Higgs field phi, and we look at a moduli space of connections, and I think this should also work for a more general family where the bundle is allowed to vary as a function of t and stuff like that. But we just wrote this down in this case. Yields a construction which corresponds to this situation, limiting, and also you have to choose an ultrafilter, limiting harmonic phi map. So I'm using this kind of capital phi here for the Higgs field. This smaller phi is the multi-value differential, which is the spectral curve of the Higgs field. I mean, the values of the differential are just all the different eigenforms of capital phi here. And you just get a limiting map to some building. To some kind of R building. And in the SL3 case, this is modeled on the apartment system is just R2 with the S3 group of symmetries and so on. But I mean, in general, I think this should work for any kind of group or something like that. You know, in general, you'll get the apartment system is going to be the one which happens for the Bruatitz buildings for that group, basically. So we get a limiting harmonic phi map. But that's just kind of a formal thing where it actually depends on the ultrafilter to take the limit and so on. Where roughly speaking, the distance from h of p, h of q, is some kind of limit from, it's just that it has to take the ultrafilter limit, but it's the limit of 1 over t times the log of the absolute value of rho t. So it's basically the scaling factor c here. It's just that we need to take a limit, and you might want to take a lim sup or something like that. If the limit equals if the limit exists, then any ultrafilter limit is going to be equal to that limit. If it's just a lim sup but not necessarily a limit, which actually happens in fact notably at the boundaries along the wall, then the ultrafilter limit might be different from the lim sup, for example. But you know, it's roughly speaking some good approximation to the WKB exponent. This is just the distance in this building. Okay, this is just kind of a formal thing, which I think basically sort of puts into detail what was always kind of a hope, I think, ever since the theory of harmonic maps to buildings came about. I mean, this is sort of what you think of them as corresponding to in terms of as related to, say, harmonic maps to symmetric spaces. But then the question is, what about, let me try this operation here. I should stop. Sorry. So then the statement which we like to show is just that we have the same universal property. So but let me put this as a conjecture. So the conjecture is that there exists a versal. In fact, it's for some reasons which I can't explain. There exists a versal harmonic phi map to a building from x tilde into some b, some building depending on phi. So this is only supposed to depend on the spectral curve, so it's only supposed to depend on this multi-value differential, but it's supposed to have this universal property, but except it's only a versal property. Which is that if we have an actual map to a building obtained by that type of a condition, then it's supposed to factor. The difficulty here is that x has a real 2 dimensions. This guy, for bigger groups, has sort of an arbitrarily big dimension. So this can definitely not surject onto this guy. So on the points here, the many points here, which don't come from points here, there's no uniqueness here. I mean, and you can actually construct situations where you can see that you shouldn't expect a uniqueness of this map. So that's why it's a versal guy. And so we could just show that in one particular case in our preprint. So we think this may be so let's say maybe a pre-theorem in progress. Maybe a 3 theorem in progress in the SL3 case. In the SL3 case, but the idea is to kind of cheat anyway. Here we're cheating a lot, you might say, because we're using the fact that the tree is going to be a quotient of x. Okay. So the points in the tree, we know what they are. They're leaves inside x. Here we maybe cheat a little bit, which is that there's actually, in the case of SL3, this has dimension 2, and this also has dimension 2. So this guy is actually going to cover, some percentage of the points here, you might say. I mean, it's going to cover some open sectors inside here. Let me just finish by maybe the drawing of what this actually looks like. So this is a theorem in the BNR in the example, so CR preprint. But let me just say what the homoharmonic map looks like in this example. This example, we have the spectral curve has 2 different ramification points. And there's what's called a caustic line joining these 2 guys. This region inside here, and these are the Gaudio-Mornitsky spectral network curves. This region here, bounded by the Gaudio-Mornitsky spectral curves, maps into here. The rest of the picture actually maps down here. Okay. And this whole thing maps into sort of an initial piece of a building. And the idea is that then you can fill it out to make an actual building. But the initial piece of the building is actually pretty easy to think of. You just take 2 sheets of paper and glue them together along this region. Okay. So let's just take 2 sheets of paper and glue them together along a region that looks like that. So just put some glue here and glue your 2 pieces of paper together. So they're not glued together down here, okay? And this region here, it sort of folds over along this caustic line. And the stuff above here goes to the back sheet, and the stuff below here goes to the front sheet. Okay. So that's the example we know how to look at. And then based on what's going on here, trying to redo the proof a zillion times, we think we may know how to see what to do in the general case for SL3. So I'll stop.
Questions? Yes.
Is this compactification compatible with mirror symmetry in a sense that before compactification we can view Higgs bundles for group and Langland's dual as mirror pairs, and what happens after compactification?
Maxime.
I think mirror just change abelian variety by dual, but doesn't change the base of each.
Yeah. I don't understand this at all, obviously, but my vague understanding is that we should actually somehow or other think, but I don't know how this is supposed to work, but somehow or other more think of this guy as being mirror dual to this guy. Is that?
No, I think mirror dual is representation of by 1 to mirror dual group. That's it.
Okay. Oh, so you think that if you do mirror dual here, then you should get a mirror dual
I
here?
don't do mirror symmetry at all in Higgs size or connection size. Just on the baiting, yeah.
But then what happens over here? I mean.
No, actually mirror symmetry is actually it is clear here.
You look with terminal and you put it in 0.
But this is the case when the surface is compact. If you have punctures, the story is more complicated.
No, it doesn't matter. Punches you don't play your role.
It does, you have potential to have that.
Well, the question is if mirror symmetry is spoiled by adding divisors and finishing. So that's it.
what happens when, well, I think when you, I mean, I'm not sure, I think, at least in some way, you can think of going from a symplectic guy to a Poisson guy, right? Is that true? When you add the divisor and infinity? Maybe at least in this picture.
Yeah, I remember suggested some time ago just because you have for the last thing you have problems that curve is too low dimensional, yeah? Is it possible to extend to some kind of high dimensional complex variety and your family of connections?
If you try to replace x by a higher dimensional variety,
Yeah, or in neighborhood with curve is high dimensional variety. Just pure analytic equation. If you get family of connections, can you get?
you mean try to look at just an analytic neighborhood of the curve. I don't know about that. I mean, yeah, I see. I think I understand your remark a little better. I'm not sure. I mean, you know, the real problem. I mean, certainly the real problem with this whole thing is that we don't have any way of saying what the points in the building, which are not touched by points of curves, should actually correspond to. That's the real kind of a question here, which, you know, in the tree case, you can say the points of the tree correspond to leaves, so there's some geometrical thing. So that's a good question. I don't know. I don't know.
Yeah, and I think it's also this Jan just remarked, we try to understand how to calculate DT invariance through this character variety. It's actually leads to a very neat question. We should start algebraic maps of C star to character variety. Yeah, and this has the same, it gets some new algebraic variety which has the same dimensions. Original character variety and you get some kind of algebraic change of coordinates which is exactly.
So you think that like sort of counting C stars inside here? The space of C stars inside here.
Degree polynomials, Laurent polynomials, and its variety has the same dimension as the character variety. And it maps in kind of two different ways. You get some algebraic change of coordinates, and that's will be DT invariance at the end of the day.
You mean the two different ways are the two endpoints somehow or other? Or?
Yeah, kind of, yeah, 2 endpoints new for all, like maybe 2 devices to infinity, yeah. Yeah, so
you're looking at C stars, so there's going to be 2 different points here. So you're thinking of this.
No, C star will, will connect 2 different points, but the interior of C star will be exactly inside character variety.
Yeah, okay, but so that's going to give you like a correspondence between the divisor and itself somehow or other. Like maybe a Hecke type of correspondence or something.
Yeah, no, just it's kind of neat question here too.
Yeah, okay.
Depending on the conditions to Laurent polynomials.
Okay, good. So we have now we have a correspondence between this divisor and itself, which is the moduli space of C stars mapping in 2 different ways to.
More questions? Okay, thanks very much.
Yeah. Okay. Thank you.